There's a star out there in the constellation Cygnus the Swan, about 1,400 light-years away from Earth. At first glance, through a telescope, it appears as nothing special, just one of hundreds of billions of points of light scattered across the Milky Way. This particular star started behaving in a way that had people scratching their heads. Its light was not steady. It was not even flickering the way you would expect from a planet passing in front of it. Something else, much more strange, was happening here. The brightness of the star was dropping by huge amounts, sometimes by as much as 20%, and then bouncing back in brightness days or even weeks later. That's a huge dip in brightness, and it seems something more than a transitioning planet was causing this. For comparison, if a planet the size of Jupiter crossed in front of a star, you'd expect maybe a 1% dip in brightness. The transit method is one of the main ways used to find planets outside our solar system. It works like this. If a planet passes directly in front of its star from our point of view on Earth, the star's light will dip slightly for a short time. This tiny drop in brightness can be measured with sensitive instruments. By watching these dips happen repeatedly, it's possible to figure out the planet's size, how often it orbits its star, and even clues about what its atmosphere might be like. The bigger the planet, the more light it blocks, and the deeper the dip in brightness appears. But the usual explanations don't seem to fit. It was not the neat, rhythmic pattern of an orbiting world. It was not the kind of dimming you'd expect from dust or gas clouds drifting by. It was erratic, unpredictable, and it kept happening. The more people looked, the stranger it got. Over the years, the star's overall brightness seemed to be slowly fading, as if something enormous, and we mean truly enormous, was gradually blocking more and more of its light. And then came the theories. Some thought it might be an enormous swarm of comets, all breaking apart and scattering dust in front of the star. Others proposed huge clouds of material from shattered planets. And then there was the wildest idea of them all. What if this was not a natural event at all? What if we were looking at the handiwork of an advanced civilization? Something massive, maybe even a structure built to surround the star and capture its energy. Something like a Dyson sphere. If that idea sounds like pure science fiction, it's worth remembering that the concept of a Dyson sphere did not come from Hollywood. It came from physicist Freeman Dyson back in 1960. He proposed that an advanced civilization might eventually need so much power that it would make sense to build a massive structure around its star to harvest its energy directly, and a star would be the ultimate power plant. Now, in reality, a solid shell completely enclosing a star is probably impossible to build. The stresses, the heat, the sheer engineering required would be on a scale almost impossible to imagine. But a swarm of giant satellites, mirrors, and collectors orbiting in formation could achieve the same effect. From far away, that would look like a star gradually dimming, its light blocked in irregular patterns. And that's exactly why Tabby's star got so much attention. Its weird flickering seemed almost custom-made to fit that theory. It wasn't just one short blip of light, this was a pattern of unpredictable dimming, happening again and again over the years. Some of the drops were so deep and sudden that natural explanations started to sound forced. The story really exploded in 2015, when data from the Kepler Space Telescope revealed just how bizarre this star's light curve really was. Kepler had been staring at over 150,000 stars, looking for the tiny dips in brightness caused by planets passing in front of them. Most stars were boring and predictable. Tabby's star was neither. The light curve looked like a heartbeat gone haywire, with deep plunges and slow fades scattered at random. Once the data went public, the internet did what the internet does best. It latched on to the most exciting possibility. Articles popped up asking if this could be the first real evidence of an alien megastructure. Tabby Boyajian, the astronomer whose name the star now carries, never claimed it was aliens, but she admitted the behavior was unlike anything ever seen before, and that was enough to fuel months of speculation. The idea of a Dyson sphere orbiting this star captured people's imaginations. Just picture it. A civilization so advanced that it could dismantle entire planets, use the raw materials to construct an enormous array of collectors, and then live off the nearly limitless energy of its star. From our point of view, it would be a glittering halo of machines, blocking the star's light in strange, shifting ways. But the real question was, could something like that actually be what we were seeing? Even more baffling, long-term observations revealed that the star's overall brightness had been slowly declining over the course of decades. That's not something stars like this are supposed to do. It was as if some vast shadow was slowly spreading across it, layer by layer. Imagine watching the sun and seeing it dim by a quarter, not just once, but several times over a few years, and in no predictable rhythm. That's the kind of unsettling behavior Kepler recorded. It didn't match the signature of a planet, a star spot, or even the occasional dust cloud. This was something else entirely. The irregularity was key. Planetary transits follow clockwork. Dust clouds tend to scatter light in predictable wavelengths. But Tabby's star? It seemed to be playing by rules we didn't understand. Each dip looked different, some sharp, some gradual, some jagged. It's as if pieces of some colossal, uneven structure were drifting past in no particular order. And when people compared it to the hypothetical signature of a Dyson swarm, the resemblance was hard to ignore. A loose collection of massive objects orbiting the star at different speeds and distances would produce exactly the kind of irregular dimming Kepler recorded. Still, the more cautious minds in the astronomy community kept repeating, extraordinary claims require extraordinary evidence. And so began the hunt for a natural explanation, something that could reproduce these bizarre light patterns without invoking alien engineering. But as we'll see, that search would only deepen the mystery. When that Dyson sphere idea went viral, it grabbed everyone's attention. It sounded like it was possible we just discovered an advanced extraterrestrial civilization. Yet the natural explanation still had to be eliminated first. One of the earliest theories was a swarm of shattered comets or planetary debris near the star, which would look like dust and debris clouds drifting into the telescope's view. That would explain the weird dips, but to block 20% or more on a regular basis required an absurd number of comets, or some really giant pieces of rock. Which brings us to the next idea, that a planet had exploded or shattered, scattering debris into the star's orbit. But that should have produced a glow of warm dust that we'd be able to detect in infrared light. That glow has never been found in the telescope data. Some thought the star might be just a peculiar variable type, like it had internal processes that made its brightness change unpredictably. Again, that didn't line up with how stars of that kind behave. There was no rhythm, no pattern, nothing that matched those explanations cleanly. Then something new recently emerged. Observations from NASA's Spitzer and Swift telescopes, along with ground-based data, revealed a clue. The dimming was stronger in blue and ultraviolet light than in red or infrared light. That kind of light filtering is a telltale sign of dust. More detailed modeling suggested there could be a lopsided ring of dust orbiting Tabby's star, blocking the light unevenly and shifting over time. In this scenario, different parts of the dusty ring drift across the star and cause the strange flickers and fades we see. Still, the dust ring idea does not explain everything. The long-term fading over decades is odd. The short-term dips have a different color signature than the slow fade. The dust in those ring models should be small and short-lived. It takes constant replenishment. And even then, it doesn't match every event. And don't forget that these would have to be huge, thick clouds of dust and debris crossing in front of the star. It's not a very good explanation, but the dust ring is the current best fit for much of the behavior. But it doesn't rule out something we still cannot imagine, like advanced technology from a super-intelligent extraterrestrial race. While the dust ring idea was gaining traction, another star began behaving strangely. This time, it was not an obscure object that no one had ever heard of. and nearly everyone has heard of the famous Betelgeuse, one of the brightest, most famous stars in the night sky, the red supergiant that forms the shoulder of the constellation Orion. In late 2019, Betelgeuse began to fade. At first, the drop in brightness was subtle, but over the weeks that followed, it dimmed more and more until it was only a fraction of its usual brilliance. This was shocking because Betelgeuse is a massive, unstable star nearing the end of its life. Theories immediately exploded across the internet. Was this a warning sign that Betelgeuse was about to go supernova? Would the star's death outshine the full moon and cast shadows at night here on Earth? The excitement was electric. Telescopes around the world turned their gaze to Orion. Every night, stargazers checked the familiar constellation, watching the red glow fade as if something cosmic was about to happen. The truth, as it turned out, was less apocalyptic, but still fascinating. Images from high-power telescopes revealed that Betelgeuse was partially obscured by a massive cloud of dust. It seemed the star had ejected a chunk of its own atmosphere, which then cooled and condensed into dust, blocking its light from our view. But the similarities to Tabby's star were eerie. In both cases, something had interfered with the star's light in a way that could be mistaken for something artificial, at least at first glance. And in both cases, the universe offered us a humbling reminder. Nature can be every bit as strange, complex, and unpredictable as anything we can dream up. But just recently, in July 2025, an incredibly shocking discovery was made about Betelgeuse. Much to everyone's surprise, it turns out this famous red supergiant star has a hidden companion star orbiting nearby. This companion had remained elusive for years, but new observations revealed its presence. This discovery sheds new light on Betelgeuse's strange behavior. The gravitational dance between the two stars may help explain the irregular dimming and massive bursts of material we've seen. Interactions between the pair could be stirring up gas and dust, sometimes sending clouds between Betelgeuse and us. It also means that now Betelgeuse is part of a binary system, not a lone giant star. That changes how we understand its evolution and what might happen when it eventually dies. Rather than a simple supernova, the companion could influence the final explosion's shape and brightness. The idea that a hidden partner star is shaping Betelgeuse's story reminds us that the universe is full of surprises. Even stars we thought we understood can still hold incredible secrets. Betelgeuse having a companion is just one of many incredible discoveries made recently. Far out in the cosmos, around 5 billion light-years away, lies a black hole that could be the most massive ever found. Inside a distant galaxy, SDSS J1148+1930 is a monster black hole that weighs about 36.3 billion times the mass of our Sun. That puts it close to the practical upper limit of how big a black hole can get. To put this into perspective, the black hole at the center of our Milky Way is just 4.3 million solar masses, tiny by comparison. This one is so huge it goes beyond the term supermassive. It belongs to a category that can only be described as ultramassive. Supermassive black holes, with at least 1 million solar masses, are thought to sit at the heart of every full-sized galaxy, pulling everything in the galaxy into orbit around them. Theoretically, there's no limit to a black hole's growth, but in the 13.8 billion years since the universe began, it's thought that one could only realistically reach about 50 billion solar masses. Finding extreme examples like this is one way to test those limits. The discovery was made thanks to a phenomenon in the night sky called the cosmic horseshoe. It looks like a glowing horseshoe wrapped around a bright central blob, caused by a rare cosmic alignment known as gravitational lensing. In this case, a massive galaxy in the foreground bends and magnifies the light from another, more distant galaxy behind it. Some black holes may be heavier. For example, Tan 618 was once thought to be about 66 billion solar masses, before later calculations revised it down to about 40 million. But those figures are less certain. This new one's mass is far from confidently measured. What makes this find even more fascinating is that this is a fossil galaxy. This means it was once part of a galaxy cluster, but over time, all the galaxies merged into one colossal galaxy. Along the way, each central black hole merged as well, eventually creating this single, ultramassive, 36 billion solar mass black hole. It offers a rare glimpse into one of the biggest mysteries in astronomy: how black holes grow to such unbelievable sizes. In the cosmic horseshoe, we may be looking at the final stage of both galaxy growth and black hole evolution. It's pretty safe to say that we have no idea what a black hole is, what's going on inside, or if it's something else completely. It's not like we can directly image one, but at least we can now get images of their huge shadows in space. In 2019, astronomers grabbed the first ever image of a black hole, and a new polarized image shows powerful magnetic fields wrapping around a huge black hole shadow. This supermassive black hole is some 55 million light-years away from us and is bigger than the entire solar system. We're going to use this massive black hole for a simulation that involves you and a friend, but we'll get to that in a bit. You know the whole thing about nothing being able to escape a black hole? Well, is this really true? When a black hole eats up a star or a bunch of gas, they generate a powerful flow of high-energy particles close to the event horizon, the ring of fire called Hawking radiation at the edge. And if a black hole is really chewing on something, like a massive star, powerful X-ray jets shoot out, and the black hole becomes a quasar, the brightest objects in the universe. Who says light can't escape it? Well, now we have another argument about nothing being able to escape a hungry black hole. This is because astronomers captured a neutron star in an elliptical orbit around a black hole that survived being swallowed completely. However, the dead star didn't get away from the black hole unscathed. Astronomers captured images of massive X-ray flares being belched out by the black hole as it was eating the star's material. The star is trapped on a 9-hour elliptical orbit around the black hole, and at its closest orbit, the black hole rips off more of the star's material and becomes bigger. It will try hard to get away, but there's no escape, as the black hole will eat it more and more until there's nothing left. So now we all understand how powerful a black hole can be, even swallowing each other. Now you might be wondering what the closest one to Earth is, and if we're in any danger of a black hole eating us sometime soon. Just recently, scientists discovered one of the smallest black holes ever found, and it just so happens it's also the closest to Earth. Astronomers have named it the Unicorn, because so far it's the only one of its kind, and it's in the constellation Monoceros the Unicorn. It's about 3 times the mass of our Sun, which is tiny for a black hole. And it's about 1,500 light-years from Earth, which means you don't need to worry. It's not going to come and swallow us up anytime soon. That's because black holes don't usually move and sit in one place, eating up everything that gets too close to them. But that doesn't mean they can't move. And here's a scary thought. In 2021, researchers got a big surprise when they discovered a supermassive black hole racing across the universe at 177,000 kilometers per hour. The big mystery is that astronomers don't know why the black hole, which is 3 million times heavier than our Sun, is speeding through the center of the galaxy about 230 million light-years away. Now, that sounds crazy, and it sounds fast, but in 2017, scientists clocked another supermassive black hole hurtling through space at 7.2 million kilometers per hour. An enormous force would have to be responsible to get these things moving through space that fast. Maybe what we are seeing is the result of 2 black holes colliding, the massive collision sending the other flying wildly through space. So now we've all learned what happens when something gets too close and is sucked into a black hole. So what happens to a person, and could you survive the trip? Now we've all heard that if you somehow get sucked into a black hole, you would be stretched out or spaghettified, maybe even crushed or, well, you get the idea. Now this might be true if the black hole was small enough, But a black hole, let's say 30 to 100 times more massive than the Sun? That's where reality becomes really strange. The moment you entered a black hole, reality would split you in two, or clone you. In one of these realities, you would be incinerated, and in the other, you would plunge into the black hole and fall through it without being harmed. How is this possible, you ask? Well, a black hole is a place where the laws of physics break down. Einstein said that gravity warps space itself, causing it to curve, and space-time can become so warped that it twists in on itself. Yes, we know that's a lot for the mind to wrap around, so it's time for a thought experiment. In the beginning, we said we were going to run a simulation involving you and a friend. Let's say that you both signed up to go on an adventure to the nearest black hole. One of you will go in, and the other will be an observer. You've flipped the coin. Your friend is going to watch you in horror as you plunge toward the black hole while they remain floating away at a safe distance. Now, this is where it gets weird. As you accelerate towards the event horizon, your friend sees you stretch and contort as if they were looking at you through a giant magnifying glass. But as you get closer to the horizon, you appear to move in slow motion, and as you reach the horizon, you remain there, motionless, stretched across the surface of the horizon, and the heat begins to engulf you. Your friend sees you slowly obliterated by the stretching of space and the ring of fire called Hawking radiation. Before you get a chance to cross over into the darkness of the black hole, you are reduced to ash. Game over. But don't plan your funeral just yet. We need to view this scene from your point of view, because something even stranger happens. Nothing. That's right. From your perspective, you would sail straight into the ominous black hole without so much as a scratch. No slow stretching and no scalding Hawking radiation either. The reason is that you are in a free-for-all, and therefore you feel no gravity. If the black hole was smaller, you'd have a problem because the force of gravity would be stronger at your feet than your head and stretch you out like spaghetti. But something way more massive than our Sun, the forces would be small enough you wouldn't notice them. But the sad and lonely part about this adventure is that you would live out the rest of your life pretty normally until you reached the singularity. But what's wrong with your friend? And why are they telling everyone that you've been barbecued to a crisp by radiation outside of the horizon while you're chilling inside the black hole? Actually, you really were burnt to a crisp at the horizon, and you are inside the black hole at the same time. This is because the laws of nature require that you remain outside the black hole as seen from your friend's perspective, and quantum physics demands that information can never be lost, and all information that accounts for your existence has to remain on the outside of the horizon. However, the laws of physics also require that you sail through the horizon without being fried by hot particles, otherwise you would be in violation of Einstein's theory of general relativity. Now, some of you are going to say, no way. And you have to admit, it's a conclusion that seems nonsensical. How can a black hole clone me, you're asking? Physicists called this mind-bending conundrum the black hole information paradox. But in reality, there's no paradox, because no one ever sees your clone. Your friend only sees one of you, and you only see yourself. Neither one of you can compare notes, and no one really knows what happens. And it doesn't matter if we try to send someone or some spacecraft inside of a black hole to relay back some data. Once inside, there will be no way for a signal to get out, and you'd be lost forever. But what an awesome trip it would be. So what about the mystery of the black hole in the middle of the Milky Way galaxy? For years, it was widely accepted that Sagittarius A is a black hole in the middle of the Milky Way galaxy. However, some astrophysicists from Italy now say the object, which is as big as 4 million suns, might not be a black hole after all. The reason is that a huge gas cloud came close to the black hole. The gravitational forces of Sagittarius A should have eaten the cloud, but the cloud of gas survived with an issue. Could it be the home of Cthulhu? Well, while we love to joke about this, the answer might just be as mysterious. Some scientists say that the center could be a big bundle of that incredibly elusive stuff they call dark matter, which is invisible and thought to account for 80% of the total matter in the universe, but cannot be detected because it doesn't interact with light. Now scientists have proposed that black holes themselves could be formed out of dark matter, which would explain why they can form so quickly before the galaxies around them. And one day, that might be proven to be true. Stars are born in clouds of gas and dust called nebulae. As gas molecules and dust particles come together, they collapse under their own gravity and heat up to form a protostar, the initial phase of a star's evolution. As a hot core forms and gathers material, it continues to heat up, and once it reaches about 15 million degrees Celsius, a star enters its main sequence phase and nuclear fusion begins. That's how a star will spend about 90% of its time. Scientists think that to sustain nuclear fusion, a star can be no smaller than 8.7% the diameter of our Sun, which is roughly 1.39 million kilometers. With a bit of calculations, these 8.7% translate into about 120,000 kilometers. But that's still a bit smaller than Jupiter, which is, like most stars, made of hydrogen and helium. So why isn't it a star? Jupiter just isn't massive and dense enough. It lacks internal pressure and temperature to sustain nuclear fusion. Generally, the more mass a star has, the shorter its lifespan. A star the size of our Sun will stick around for roughly 10 billion years, but one that's 10 times more massive than that would only live for about 20 million years. But what happens after that? Approximately 97% of stars will become white dwarfs. And just recently, scientists discovered a miniature white dwarf around 4,300 kilometers wide and 45,700 degrees Celsius in temperature. That's just a bit larger than our Moon and is roughly the distance from Los Angeles to Washington, D.C. But don't be misled by the tiny size of this star. It has 35% more mass than our yellow dwarf Sun. In fact, 1 teaspoon of matter from a white dwarf star would weigh as much as a 5.5-ton elephant on Earth. This makes it the smallest and yet the most massive white dwarf discovered so far. This white dwarf also makes a full 360-degree rotation in just 7 minutes, which is 200 times faster than our planet rotates. But could we survive living near a white dwarf? As our Sun will eventually become a red giant when all of its fuel is used up, it'll transform into a white dwarf. But let's say, for example, that planet Earth was placed in the habitable zone of a white dwarf. Generally, white dwarfs are bright enough to have habitable zones around them, but too dim to extend the habitable zone far enough to where we are now from our Sun. A habitable zone around a white dwarf begins at about 1/100th the distance that our planet is to the Sun, and that's quite dangerous because of the gravitational force. That gravitational force would tidally lock our planet. Although a tidally locked planet would look interesting because of the permanent night side and day side, the gravitational pull of a dead star will heat and flex Earth a lot. The closest planets, Mercury and Venus, will be, most probably, obliterated. But that's just the beginning. Over time, white dwarfs cool and emit less light, thus shifting their habitable zone closer and closer to a dead star. This means all the water on Earth would freeze, and with less light, we'd be bathed in high-energy radiation. If that happens, our planet would become more like Venus, with an atmosphere filled with carbon dioxide. Now, what about the stars that are bigger than white dwarfs, and how do we even measure the size of a star? It turns out that scientists can tell how big a star is by knowing its surface temperature and luminosity, which is the energy that a star emits. They've even come up with a special diagram that can predict the size of a star depending on the above-mentioned criteria. Although we think something's hot if it's orange or red, with stars, it works the other way round. The hottest stars out there have blue hues, while cooler stars appear to be red. And this representative of a very rare stellar class of stars is just an example of this rule. It's one of the hottest stars ever discovered. With a radius half that of our Sun, the surface temperature of WR102 is 35 times hotter, and it's got a blue color. But that's still quite smaller than our Sun, and the universe has a lot more stars that are both bigger and more interesting. HD 140283, or Methuselah, is a star that's 1.7 times larger than our Sun. It also has a mass roughly 0.8 solar masses and is about 5 times more luminous than our star. Methuselah is one of the oldest yellow subgiants that we've ever discovered. In fact, it's so ancient that scientists' initial calculations showed it was 16 billion years old, which is odd if the universe is only 13.8 billion years old. But even according to recently revised estimates, this star still seems to have been born shortly after the universe itself. The next star is just a toddler compared to the previous old-timer, but it has some other features that make it stand out. R136A1 is about 30 times our Sun's radius, but it's one of the brightest stars out there. If our Sun was replaced by this star, you probably wouldn't be able to go out without high-quality sunglasses on a sunny day. Breaking the earlier accepted limit of 150 solar masses, this star is a whopping 265 times as massive as our Sun. This number is so huge that it potentially points to the most massive star out there that makes all other known stars pale in comparison. Sadly for this star, due to its extreme mass, temperature, and luminosity, it's doomed to a short life. It's believed to be 1 million years old, and it only has about the same amount of time left before it goes hypernova. R136A1 is a real heavyweight, but its size is still quite tiny compared to a bluish-white supergiant called Alpha Cygni. This monster is roughly 200 times the size and at least 50,000 times more luminous than our Sun. However, Alpha Cygni is just about 19 times as massive as our star, and now imagine how this giant would shine seen from the Earth if it were our Sun. Now let's go to the red supergiants. Meet Antares, a star that's about 680 times the Sun's radius, which is more than 3 times the distance from Earth to the Sun. What this means is that if one day our star was replaced by Antares, our planet and even Mars would have been swallowed by it. But if it was a bit further, the red supergiant would look like a big burning ball of hot plasma, about 1100 times brighter than the Sun. But even a star of this size is nothing compared to the largest one we've been able to detect. Stephenson 218 currently holds the title of the biggest star and is the most luminous red supergiant in the entire universe. The star's radius is nearly 2,150 times the Sun's radius, which is a number that can hardly be grasped by our brains. 3 billion kilometers. Our Sun has a volume of about 1.3 million Earths. Now consider this. Stephenson 218 can fit inside a whopping 10 billion suns. To say it's a huge star is an understatement. Nevertheless, even that is not the limit to how big a star can grow. A hypothetical quasi-star, known as a black hole star, could be much, much larger. Scientists believe these existed at the dawn of the universe, and their size could have been approximately 10 billion kilometers. To give you a bit of perspective, it took nearly 10 years for the New Horizons probe to get close to Pluto, and it would need 5 more years to get out of the quasi-star if it was trapped in one. If one still existed, a quasi-star would produce as much light as a tiny galaxy. That would be a breathtaking phenomenon to contemplate. There are many stars that are much more intriguing than our boring average-sized Sun is. And while it would be a lot more fun to look at those fascinating stars from the Earth, life on our planet is too sensitive for such entertainment. Even the slightest changes in the temperature, radiation, and light could mean an absolute disaster for us. May other stars be a billion times brighter, hotter, or bigger, we're still a billion times luckier, because we can admire these huge bright monsters through telescopes and live side by side with probably the most favorable star for life. A neutron star is one of the most exotic objects in the universe. Its formation is an event of galactic proportions. Every time a massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel, the thermonuclear reactions in its core cease. The core can no longer withstand its own gravity and begins to collapse at an incredible rate. This causes its temperature to soar to billions of degrees. As a result, the star's outer layers expand and cool simultaneously, turning it into a red giant. When the temperature and density in the core reach a critical point, a supernova explosion occurs. Afterward, all that remains of the once massive red giant is its core, now a neutron star. The mass of a star like this is typically around 1.4 times that of our Sun, but its size is truly astonishing. Its radius is only 6.2 to 7.4 miles, nearly 70,000 times smaller than the Sun's radius. Imagine the Sun shrinking in size until it becomes a sphere small enough to fit within New York City, which is about 35 miles wide. Compressing an object 870,000 miles in diameter into something just over 6 miles across has a massive effect on the matter that makes up the object. Neutron stars are a striking example of this. According to NASA, just 1 teaspoon of neutron star material would weigh about 1 billion tons on Earth. That's equivalent to the mass of 3,000 Empire State Buildings or the entire human population. This makes neutron star material the densest substance we can observe in the universe. It has such an unbelievable density that if, under some fantastic circumstances, a piece of it the size of a sugar cube was placed on Earth, it would instantly punch through any surface, drilling downward through the layers of the planet until it reached the core. Compared to this, the density of everything around us is practically negligible. Another astonishing property of a neutron star is its temperature. On average, its surface is heated to 600,000 to 1 million degrees Celsius, and right after its formation, it can reach a mind-boggling 10 million degrees Celsius. That's about 1,800 times hotter than the surface of the Sun. Yet, despite these extreme temperatures, the surface of a neutron star remains solid. Scientists believe it's covered by an iron crust about 0.6 miles thick. What lies beneath remains a mystery. How matter behaves under such temperatures and pressures is impossible to replicate in laboratories, leading to various theories. Some scientists suggest that inside neutron stars, protons and neutrons break down into even more fundamental particles called quarks. If true, the depths of these objects could be composed of a mysterious quark matter. Another mind-blowing feature of neutron stars is their immense gravity, caused by their extreme density. The gravitational pull of Jupiter or even the Sun, which holds an entire planetary system in orbit, pales in comparison to what happens near a neutron star. Its gravity is beyond comprehension. To grasp the extent of its power, imagine your spaceship somehow landing on a neutron star's surface. To take off and escape its gravity, you would need to reach a speed of 93,000 miles per second, half the speed of light. For comparison, escaping the Sun's gravity only requires a speed of 383 miles per second. If by some fantastical means you dropped an object weighing less than a pound onto a neutron star, it would accelerate so much upon impact that the energy released would be equivalent to the explosion of 1,000 hydrogen bombs. The only stronger gravitational pull found in the universe belongs to black holes. Neutron stars are so incredible that they're rightfully considered among the most exotic objects in the universe. However, as it turns out, they come in a variety of types, and some are so unique that when scientists first discovered them, they thought they might be signs of extraterrestrial life. In 1967, British scientists detected a strange phenomenon. Something or someone was sending signals to Earth from space. These signals arrived with astonishing regularity, as if something in the distant cosmos was switching on and off with precise timing. At the time, it was interpreted as a possible message from extraterrestrials, since nothing known at the time could produce such signals. Later, it turned out that these signals came from a pulsating radio star, an object emitting rhythmic pulses, which is how pulsars got their name. A neutron star is not only an extremely dense and incredibly hot object, but also one that rotates at an extraordinary speed. This effect arises due to the conservation of angular momentum. To better understand how this works, imagine a figure skater spinning on ice. When they pull their arms close to their body, their rotation speed increases dramatically. A similar process occurs with a neutron star. As a star collapses under gravitational forces, its diameter shrinks and it begins spinning faster and faster, reaching dozens of rotations per second. Over time, neutron stars generally slow down. reducing their spin to about 8 rotations per second or even less. However, if a neutron star has a companion, such as a white dwarf, the situation changes. By absorbing material from its partner, the neutron star retains angular momentum, which can accelerate its rotation. This spinning acceleration effect can make some neutron stars rotate dozens or even hundreds of times faster than regular isolated neutron stars, transforming them into pulsars. As they spin, pulsars emit powerful, destructive beams of energy from their poles, producing sweeping lighthouse beams composed of radio waves, visible light, X-rays, and gamma rays. The flashes from these beams are detected on Earth, creating a cosmic beacon effect that resembles an artificial signal sent from deep space. Moreover, pulsars pulse with astonishing precision, allowing them to function as highly accurate cosmic clocks. Some are so stable that their periodicity rivals atomic clocks. It's hard to imagine an object with a radius of just 6.2 miles spinning faster than helicopter blades, but this is far from the limit for neutron stars. In the distant Sextans constellation, 5,000 light-years from us, scientists have discovered a true monster, making ordinary neutron stars seem almost tame in comparison. Its name? PSR J09520607. This is the heaviest and one of the fastest spinning neutron stars ever discovered. Normally, neutron stars have a mass of around 1.4 times that of the Sun, but this pulsar's mass is nearly 2.4 solar masses, bringing it close to the point of no return. According to recent calculations, if a neutron star reaches a critical mass of 3 solar masses, it can no longer resist its own gravity and will ultimately collapse into a black hole. If a neutron star rotates at a normal speed, say no more than 30 times per second, it only needs a mass slightly above 2 solar masses to collapse into a black hole. However, for pulsars, the situation changes. Rapid rotation increases a star's resistance to collapse. PSR J09520607 is one of the fastest pulsars ever observed, spinning at an astonishing 707 rotations per second. For comparison, the blades of your kitchen blender spin much more slowly. Thanks to this immense speed, the pulsar continues to resist turning into a black hole, but this does not last forever. For a long time, scientists sought to understand why this neutron star spins so fast and has such a massive weight. All the data suggests that it must have a stellar companion from which it actively accretes matter, increasing both its mass and rotational energy. This hypothesis was confirmed. Orbiting the pulsar at 236 miles per second is a companion star, likely a white dwarf, being slowly devoured by the pulsar. This process will eventually lead to the complete destruction of the white dwarf. Pulsars of this type are called black widows because they consume their stellar partners, growing more powerful in the process. However, everything has a limit. Even before fully absorbing its companion, PSR J09520607, given its mass approaching the critical threshold, will likely collapse into a black hole. A supermassive, rapidly spinning pulsar like this has the potential to obliterate anything caught in its gravitational field and intense radiation, including the solar system. If J09520607 were to appear in orbit around Mars or Jupiter, the closest planet would be its first victim, torn apart and consumed by its accretion disk. The remaining planets would be thrown off their stable orbits, chaotically drifting toward the pulsar. Earth would be doomed too. The atmosphere would instantly evaporate, and the surface would turn into a scorched, lifeless wasteland. Eventually, the pulsar would devour the Sun, and upon nearing 3 solar masses, it would collapse into a black hole, wiping out the remnants of what was once the solar system. However, even such an incredibly dangerous cosmic killer has rivals that surpasses it in certain aspects. One of them is located just 1,000 light-years away. We're talking about one of the brightest pulsars ever observed and one of the closest to Earth. This pulsar is known as Vela. and astronomers recently detected the most powerful light burst ever observed coming from it. Studies of Vela have shown that its gamma radiation is about 200 times stronger than that of an ordinary pulsar. This suggests that something unusual is happening within its pulsating polar streams, which extend 0.7 light-years into space, a distance 15 million times greater than that between Earth and the Moon. Normally, particles accelerate with specific zones around a pulsar, but these regions alone cannot explain the extreme energy levels observed in Vela. Scientists speculate that particle acceleration may occur beyond these usual zones, or that powerful magnetic fields exist outside them. Another possibility is that neutron star winds accelerate particles, ejecting them with enormous energy. The scientific community has yet to reach a consensus, and research into this pulsar is ongoing. One particularly fascinating discovery is how Vela would sound if its signals were in the audible range for humans. Like other pulsars, Vela emits regular radio bursts, pulsating approximately 11 times per second. NASA scientists recorded these signals using a radio telescope and converted them into an audio format. The resulting sound resembles the whir of helicopter blades or the roar of a car engine. Since Vela is relatively close, scientists have also been able to study its incredibly powerful magnetic field in detail. Neutron stars are known for their colossal magnetic fields. Vela's, for example, is 2 trillion times stronger than Earth's. But imagine, there are neutron stars in existence with magnetic fields 1,000 times stronger than Vela's. These stars are among the most dangerous objects in the universe. Their power is so immense that if a person were to be just a few thousand miles away from one of these stars, their body would instantly dissolve into space under the influence of a colossal magnetic field, which would disrupt the atomic structure of their body. They're called Magnetars. This is an extremely rare type of neutron star. Only 1 in 10 supernova explosions gives rise to a magnetar, a celestial body possessing an unimaginably strong magnetic field, the most powerful in the entire universe. These neutron stars can generate gamma-ray and X-ray bursts, releasing colossal amounts of energy. The strength of their magnetic field is so great that it causes a unique phenomenon: the slowing of the star's rotation to just 1 full turn every few seconds, or even minutes. Moreover, even the magnetar itself cannot withstand such extreme magnetic fields. Periodically, these fields cause starquakes on the surface of the magnetar. These quakes make the star's solid crust crack and shift, releasing an enormous amount of energy from its depths. This makes the magnetar unstable and, at that moment, more dangerous than ever. During these events, the energy ejected from its core in mere milliseconds can equal the energy the Sun emits over an entire year. If a magnetar were just 10 light-years away from Earth, the radiation from an explosion like that would instantly destroy our planet's ozone layer. Fortunately, the closest known magnetar, XTE J1810197, is located 8,000 light-years away, meaning Earth is in no danger. However, if it were just a little closer, our concerns would be justified. If this magnetar experienced a starquake within 4,000 to 6,000 light-years of Earth, the intense burst of gamma radiation could partially affect our atmosphere. The first problems you'd notice would be power outages and interference in your car's navigation system. While trying to figure out the cause of the disruptions and avoid getting lost, Earth's atmosphere would be under siege by high-intensity gamma radiation, causing severe damage to power grids and satellite communications. The consequences would be even more catastrophic if the magnetar were even closer. But what if, theoretically, a magnetar took the place of our Sun? Let's imagine that an 8-mile sphere with 1.5 times the mass of the Sun would replace our parent star. However, you wouldn't have time to realize that the Sun had dimmed strangely. Your death would be instant. A magnetar's magnetic field is a quadrillion times stronger than the Sun's. It would instantly strip Earth's atmosphere, leaving it unprotected against extreme radiation. The radiation intensity would be so immense that it would break the chemical bonds of most elements. Everything would be thrown into chaos, and the closer you are to the magnetar, the more catastrophic the consequences. Mercury would be the first victim. The magnetar would alter its orbit, pulling it in. Under the influence of colossal gravitational forces, the planet would begin to deform and break apart. As it approached within a few thousand miles, Mercury would be completely torn apart into atoms by the magnetar's ultra-powerful magnetic fields. Venus, Earth, and Mars would soon follow, meeting a similar fate. As for the gas giants, their orbits would be disrupted, but they might just stand a chance of survival. It all depends on how long the magnetar remains active. Its energy could be depleted before it has the chance to completely incinerate the remaining planets. Magnetars burn through their energy incredibly fast, and after about 10,000 years, they begin to lose their powerful magnetic fields and quickly fade. This is another reason why these objects are so rare in the universe. Pulsars, on the other hand, can exist for much longer, billions of years. This gives them enough time for rare and unexpected events to occur. For example, even such an extreme object as a pulsar can acquire its own planetary system. PSR 1257+12, located 2,300 light-years from the Sun, has 3 planets that belong to the super-Earth category, rocky planets with masses several times that of Earth. Another pulsar that was not doomed to loneliness is PSR J2007+3120, which has at least 2 exoplanets in its system. Both are several times more massive than Earth and complete an orbit around the pulsar in 1.9 and 3.6 years, respectively. This is a rare phenomenon. Out of the thousands of known exoplanets, only about 15 have been found in pulsar systems. In fact, only 0.5% of all pulsars are known to have planets. It's difficult to imagine the extreme conditions that might exist in worlds like that. The chances of surviving there are almost non-existent. But if life did exist on a planet in a pulsar system, it would be like a wild teenage party. Bright, painful for the eyes, and carrying a high risk of death. Additionally, all planets in pulsar systems share a common trait: highly elongated orbits. For example, in our solar system and in most others, planets typically follow nearly circular orbits, while planets around pulsars move in highly elliptical ones. This doesn't exactly explain how such dangerous objects manage to form planetary systems, but scientists have some theories. It's believed that these worlds may form from material ejected during the supernova explosion that created the pulsar, or from the remains of a companion star that was consumed by the neutron star. It's also possible that pulsars can capture planets passing nearby due to their immense gravity. For now, this remains a scientific mystery. While you were watching this video, more than 100 supernova explosions occurred in the universe. Some of them left behind neutron stars, while others turned into black holes. These events continue to shape the cosmos, creating new mysteries for us to unravel. We've all seen the solar system pictures in textbooks. The Sun slightly larger than Jupiter. But that isn't the right depiction of the scales. The Sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our Sun isn't the biggest star in the universe or even our galaxy. That title goes to UY Scuti, and compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling. An enigmatic ancient star with a black hole inside. It's an astronomical mystery that both puzzles scientists and can potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Stars are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. But the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond. Ordinary stars arise from the clouds of gas and dust as gravity makes the densest regions of the cloud collapse. The resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from the surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our Sun about 50 million years to reach this phase. The majority of stars will spend most of their lifespan as main sequence stars, but eventually they will either become white dwarfs if their mass isn't big enough or go supernovae. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our Sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than the Earth but about the same size. This dense sphere will slowly cool to about 18 million degrees Fahrenheit, and in about 10 billion years, the white dwarf Sun will crystallize. The process is somewhat similar to how water turns into ice. Although the material is different, in the case of the Sun, it will be carbon and oxygen solidifying. And stars over 10 times the mass of the Sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. So where does this leave them? Deep inside these stars, the extreme pressure squeezes every proton and electron so tightly they merge to form neutrons. Neutrons cannot be compressed any further, so they counter gravitational pressure and the star finds a new balance. Neutron stars are the densest objects in the universe apart from black holes. They can be just the size of a small city, roughly 12 miles, but still have a mass of the Sun. On Earth, neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes? While the star is still active, the two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squish it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counter gravity, and the star collapses on itself, just like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of ground due to the collapse of underground structures. Although with black holes, it's a gravitational sinkhole, gradually accelerating as its event horizon grows. Normally, black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air and it had small holes in it, the increased pressure inside would make some of the excess air escape. In space, something similar happens with rotating black holes. As matter spirals towards a black hole, it goes faster and faster. Because of this, about 42% of this matter can be converted into energy. And this radiation is so powerful, it can push some of that incoming material away, just like a car tire pushes the air away. This process is so efficient, the radiation emitted away surpasses the energy output from nuclear fusion in stars. Just imagine a future where we find a way to harness this energy and use it for our needs. Even supermassive black holes with a large surface area that attracts matter have this limit. They are at the center of almost every galaxy out there, and some of these supermassive black holes have been recently discovered to be much larger than we thought. That's one of the greatest mysteries in astronomy. The gradual accumulation of matter over the edge of the universe fails to explain their enormous size. But there's something that might unravel the mystery. Black hole stars, or quasi-stars, must have been the largest celestial bodies to ever exist, dwarfing even the most gigantic black holes we've discovered so far. Today, the conditions of the universe do not allow black hole stars to form. But at the beginning of time, space was packed with massive gas clouds. Within these dense regions of space, material collapsed in on itself under its own gravity, and because there was so much of it, it piled up, giving rise to baby stars of extraordinary magnitude. Although there's an idea that they may have originated from dark matter halos, invisible spherical regions of dark matter of up to 100 million solar masses where thousands of supermassive stars could form. Normally, large stars would go supernova and leave behind massive black holes. But these celestial giants weren't just large, they were so huge, their size allowed them to absorb the explosive force that would otherwise shoot the star's outer layers out into space. Instead, these ancient stars only experienced implosions, which transformed their stellar cores into tiny black holes, while keeping the outer layers intact. If you could somehow observe this phenomenon from a close distance, you wouldn't even notice any changes within the star. Now that there's a baby black hole inside a quasi-star, it starts eating it from the inside. At this point, the black hole is tiny, but it's spinning, and this creates a disk of hot material circling it at nearly the speed of light. On top of that, there's no longer a limit on how fast it can devour gas, as the star's pressure sends it straight into the black hole. The friction within the accretion disk becomes hotter and hotter, emitting tons of radiation and making the hot star glow like a small galaxy. Quasi-stars, if they existed, grew faster than any black hole we've ever observed. Eventually, within millions of years, some of them would be the largest stars and black holes in size that we know about, like Stephenson 218, UY Scuti, and TUN 618. Just how large is that? From thousands of times larger than the Sun to potentially even the diameter of our solar system and beyond. But this gargantuan size and mass also causes problems. The larger the quasi-stars become, the shorter their lifespan. Our Sun has been around for over 4 billion years, with approximately 6 billion years left in its lifespan, while black hole stars lasted for just a few million years before spectacularly exploding with unprecedented power, releasing an ever-hungry, monstrous black hole ready to drift across space in search of more material to gobble up. But what if a star like this wandered into our peaceful celestial neighborhood? Once a quasi-star found its way into the solar system, its gravitational influence would disrupt the established orbits of planets and celestial bodies. The once orderly planetary system would be in total chaos, with Earth experiencing a severe asteroid rain. The effects would start before the quasi-star entered our solar system completely. As the gigantic star swallows the outer planets and other celestial bodies, our planet would already experience a surge in temperature and luminosity, making the surface inhospitable, until finally it would consume the Earth too, although life here would long be gone by then. The central black holes within quasi-stars could have served as seeds for the formation of supermassive black holes that are at the centers of galaxies today. And they might have even played a bigger role. The dynamic processes associated with quasi-stars, such as the collapse of the central black hole and interaction with the surrounding matter, could be potent sources of gravitational waves, which in turn may have played a role in the formation of galactic structures and the distribution of stars within galaxies. But not just that, quasi-stars could have implications for astrobiology. The intense radiation from these objects might have affected the habitability of planets in their vicinity, potentially shaping the conditions for life in unexpected ways. That said, in the context of cosmic evolution, quasi-stars might have set the future by shaping the early universe in unthinkable ways. But here's another mind-blowing thought for you. Although there are probably no quasi-stars in our universe today, tiny black holes roughly the mass of an asteroid from the dawn of time might still be here. Theoretical physicists speculate that if such black holes were abundant, they could be drifting around space, sometimes ending up trapped within gas clouds. There, as new stars would be born, primordial black holes would eventually find their way into the star's cores. Even black holes the mass of Pluto would grow enormously within just a few 100 million years, a relatively short period of time in a star's evolution. So, even our Sun could have one, which the great late Stephen Hawking once suggested. If it hid a black hole about as massive as Mercury, we wouldn't even notice it, although it's very unlikely. But there's one method scientists think might help identify such cosmic containers for primordial black holes. For one, the so-called Hawking stars would be much more long-lasting. And to cool off, Hawking stars expand into red giants, something our Sun will do as it ages. But red giants with a tiny black hole inside would be a bit cooler than they normally are. Researchers have already detected about 500 abnormally cool red giant stars. To find out whether these stars hide primordial black holes within, scientists plan to observe the stars' unique vibrations as they pulsate, which could signify they indeed aren't ordinary red giants. And here's another mind-bending thought for you. Some believe that the mysterious dark matter that prevails in the universe is in fact a swarm of miniature, countless primordial black holes. And so while it's extremely improbable that a black hole like that would end up captured by a star, if there's an immeasurable number of them, at least some would. Betelgeuse, also known as Alpha Orionis, is a red supergiant star located in the constellation Orion. It's one of the largest stars visible to the naked eye and can be found forming the top left shoulder of the Hunter Orion. Betelgeuse is approximately 642 light-years away from Earth, making it relatively close in astronomical terms. This star is truly gigantic. To give you an idea of its immense size, if Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, Mars, and possibly the asteroid belt. Betelgeuse has a radius about 1,400 times that of our Sun, and a mass roughly 20 times greater. Despite this, it has a much lower density due to its expansive volume. Betelgeuse is part of a class of stars known as supergiants, which are among the most massive and luminous stars in the universe. These stars have short lifespans, burning through their nuclear fuel at an astonishing rate. Betelgeuse is thought to be around 8 to 10 million years old, which is quite young in stellar terms. However, it's already nearing the end of its life cycle. We said previously that Betelgeuse is a red supergiant, meaning that it's now in the last stage of its life. Having exhausted the hydrogen in its core, Betelgeuse is now fusing heavier elements, causing it to expand and cool, which gives it its characteristic red color. This stage is brief in stellar terms, lasting only a few million years before the star's dramatic demise. The life of Betelgeuse has been one of constant change. It started as a hot blue giant burning hydrogen in its core. As the hydrogen was depleted, the core contracted and heated up, igniting helium fusion. This process caused the outer layers of the star to expand and cool, transforming it into the red supergiant we see today. The intense fusion reactions in Betelgeuse's core are producing elements like carbon, oxygen, and eventually heavier elements like silicon and iron. Once iron accumulates in the core, it marks the end of the fusion process, as iron fusion consumes more energy than it releases, leading to the star's inevitable collapse. In late 2019, Betelgeuse began to exhibit unusual behavior. Astronomers noticed that it was dimming significantly, a phenomenon that continued into early 2020. This dimming was so pronounced that Betelgeuse's brightness dropped to about 40% of its usual luminosity, making it noticeably fainter to the naked eye. The sudden dimming of Betelgeuse sparked a flurry of scientific activity and public speculation. Many wondered if this was a sign that Betelgeuse was about to go supernova. However, while this dimming was unusual, it wasn't necessarily an immediate precursor to a supernova. Scientists proposed several theories to explain the dimming, including massive ejections of gas and dust from the star's surface and large star spots, akin to the sunspots we see on our own sun, but on a much grander scale. One of the most compelling explanations came from observations using the Very Large Telescope in Chile, which suggested that the dimming was caused by a giant cloud of dust that was ejected from Betelgeuse's surface. This dust cloud, when viewed from Earth, blocked a significant portion of the star's light, leading to the observed dimming. Fast forward to today, and Betelgeuse is once again making headlines. Recent observations indicate that the star is dimming once more. This has reignited discussions and research into what is happening with this colossal star. The recurrence of dimming events suggests that Betelgeuse is experiencing significant convective activity in its outer layers, which may be causing these variations in brightness. These dimming episodes provide a rare opportunity to study the processes occurring in the outer layers of a red supergiant. Scientists are using a variety of instruments, including ground-based telescopes and space observatories, to monitor Betelgeuse and gather data that can help unravel the mysteries of its behavior. Betelgeuse has been observed for centuries, and its brightness variations have been noted by many cultures. Ancient astronomers, including Greeks and Arabic scholars, documented Betelgeuse and its prominent position in the sky. Its name itself has roots in Arabic, derived from Yad al-Jayza, which means the hand of Orion. In literature and mythology, Betelgeuse has been a source of inspiration and intrigue. It's appeared in works of science fiction, such as Douglas Adams' The Hitchhiker's Guide to the Galaxy, where it's the home star of the Betelgeusians. Its prominence in the night sky has made it a symbol of mystery and power. But the question on everyone's mind now is, when will Betelgeuse go supernova? Predicting the exact timing of such an event is extremely challenging. It could happen tomorrow, or it could be another 100,000 years before Betelgeuse reaches the end of its life. What we do know is that as a red supergiant, Betelgeuse is nearing the end of its stellar life cycle. When Betelgeuse does go supernova, it will be a spectacular event. The explosion will be so bright that it will be visible during the day for weeks, possibly even months. It will outshine the full moon and be visible to the naked eye from Earth. This supernova will release an immense amount of energy, briefly outshining the entire galaxy before fading away. The process of a supernova is a complex and violent event. It begins with the core collapse, which happens in a fraction of a second. The outer layers of the star fall inward at speeds of up to 43,000 miles per second, generating a shock wave that propagates outward. This shock wave heats the surrounding material, causing it to glow brightly and creating the supernova's characteristic light curve. From Earth, astronomers will have a unique opportunity to study the supernova in real time, gaining insights into the processes that govern stellar evolution and death. This will also be a momentous event for amateur astronomers and skywatchers, providing a once-in-a-lifetime spectacle. That's if it happens in our lifetime. While we can't predict exactly when Betelgeuse will go supernova, astronomers are prepared to observe and study the event when it happens. Advanced telescopes and observatories around the world are ready to capture data across multiple wavelengths, from visible light to gamma rays. Public outreach and education efforts are also in place to inform and engage the public when the supernova occurs. Organizations like NASA and the European Space Agency have plans to share real-time updates and observations with the public, making this a global event that will unite people in awe and wonder. Technological advances have significantly enhanced our ability to study stars like Betelgeuse, Instruments like the Hubble Space Telescope, the Very Large Telescope, and the James Webb Space Telescope will provide unprecedented views of these distant giants. And if Betelgeuse does explode soon, the images that these telescopes are going to take will be mind-blowing. Currently, these telescopes allow scientists to analyze the light from Betelgeuse in exquisite detail, revealing its composition, surface activity, and internal processes. Future space missions and observatories will further our understanding of red supergiants and supernovae. Projects like the Vera C. Rubin Observatory and the European Extremely Large Telescope are poised to make groundbreaking discoveries, potentially uncovering new insights into the life cycles of stars and the dynamics of supernova explosions. Many of you at this point might be wondering, if the star does explode, are we any danger here on Earth? It goes without saying that when Betelgeuse does eventually go supernova, it will be an extraordinary event for observers on Earth. But the light from the explosion will take approximately 642 years to reach us, meaning we will witness an event that's happened centuries ago. The supernova will be bright enough to be visible during the day and at night. It will cast shadows. Yes, this does mean that the star could have already gone supernova, but we just haven't seen it yet. But not to worry, despite the dramatic display, Betelgeuse's supernova poses no threat to Earth. The explosion will be too far away to have any harmful effects on our planet. Instead, it will provide a unique opportunity to study the aftermath of a supernova up close and personal. Betelgeuse, the mighty red supergiant, continues to captivate us with its size, brightness, and unpredictable behavior. Its recent dimming episodes have reminded us of the dynamic and ever-changing nature of the universe. While we may not know exactly when Betelgeuse will go supernova, we do know that it will be an event of unparalleled brilliance and scientific importance. So keep your eyes on the night sky, and remember that every twinkle of Betelgeuse brings us closer to witnessing one of the universe's most awe-inspiring phenomena. Until then, we'll continue to marvel at this giant star and the mysteries it holds. Thank you for joining us on this journey through the cosmos. Make sure to stay tuned here for more exciting and mysterious things happening in the universe. And if you enjoyed the video, then give us a like. It really helps us out so we can create more amazing content for our viewers. From all of us here at Destiny, thanks for watching, and we'll see you next time.